In behavioral research, when we talk about statistical analysis, what we're often referring to is a specific type of statistical analysis called inferential statistics. Inferential statistics tell us things like how likely is it that something we see is simply due to chance. Inferential statistics are key to extending results from what was seen in a specific sample to what might be seen in the larger world. For example, if one classroom uses the new Magic Math program and has a higher mean test score than another classroom using the old curriculum, it might be due to the new Magic Math program being better, but it may also just be random chance. The two classes won't do exactly the same. One will inevitably perform a little higher than the other, even if there's really no difference between the two programs. How do you determine whether it's luck or a real effect of the Magic Math program? That's where inferential statistics come in. They help us to estimate how likely it is that some observed difference, some observed effect, is actually real and not just due to chance alone. This is extremely important for researchers if you want to generalize your findings beyond your sample. The name inferential statistics comes from the idea that a researcher wants to infer something beyond their sample. If you read a study and the author makes statements that suggest or imply that their results generalize beyond their sample, for example, they say something like, these findings suggest that students using the Magic Math program score higher, blah, 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 or schools should consider adopting the Magic Math program, blah, blah, blah. They have to report inferential statistics. Now, in practice, they may not, but they should. And as an informed consumer, you should expect them to. A key use of inferential statistics is to test hypotheses. Hypotheses are the predictions that the researcher makes before they begin their study about what he or she thinks is and is not going to happen. Research without an a priori, meaning made in advance, hypothesis is exploratory. One can't make any definitive conclusions based on exploratory studies because we can always find an explanation for something after the fact. A great example of this was some work I did years ago as part of a 5-city multi-site research team. As part of that project, a statistician in Nashville was reviewing differences between people living in these 5 different areas. He told us that there was no difference between the locations except for Seattle, which had lower levels of depression than everyone else. The lead researcher in Seattle, a truly brilliant, world-famous, incredibly smart guy, immediately explained to everyone how that made complete sense. It said, it's happy, it's friendly, people say hi to each other on the street, people move here because it's such a nice, friendly place to live. The Nashville statistician then paused and corrected himself, saying, I'm sorry, I got it backwards. Seattle has higher levels of depression than the other sites. Without missing a beat, the Seattle researcher immediately said, that makes complete sense. It's always cloudy here. You can go months without seeing the sun. We have real seasonal affective disorder problems. Everybody burst out laughing on the call. You can always find an explanation for anything after the fact. Now, sometimes people will start the study, collect their data, look at what happened, and then come up with hypotheses. What's even worse is that sometimes they'll pretend that they had those hypotheses all along. That's called cheating. If a study is exploratory, one should say it's exploratory. That's okay. On the other hand, if a study is testing a specific question, hypotheses involve 2 parts, the null and alternative hypothesis. One part is the alternative hypothesis. The alternative hypothesis is the idea you want to test. It's what you think is happening. The alternative hypothesis may be that there's a difference between groups or that your treatment or intervention works. An example of an alternative hypothesis may be that your math program leads to higher math scores in middle school students. The other part is the null hypothesis. In a nutshell, the null hypothesis is that you're wrong. Nothing's happening. The null hypothesis may be that there is no difference between the groups you're studying, or that your treatment or intervention has no effect. An example of a null hypothesis would be that your math program has no impact on math scores for middle school students. Now, this one is central to hypothesis testing, so let's highlight it in bold. If you're testing a theory, the null hypothesis is what everyone else believes. It's the existing theory. The alternative hypothesis is how you believe they are wrong, or how you would change or enhance that theory. Why don't we consider some examples of null and alternative hypotheses? Let's say that I want to test the effect of an intervention, magic math, on student learning because I think it will lead to higher math performance in 7th grade students. For that study, my alternative hypothesis would be participation in the magic math program leads to increased math scores for 7th grade students. What would my null hypothesis be? Maybe participation in the magic math program does not lead to increased math scores for 7th grade students. Notice that there are other ways this could be worded, but it always covers all of the other possible outcomes. For example, another way of basically saying the same null hypothesis would be participation in the magic math program either has no impact on math scores or leads to lower math scores among 7th grade students. In articles or chapters, you may see the null hypothesis represented by the notation H0 or H0. Similarly, you may see the alternative hypothesis represented by the notation H1, or you may see some use HA as a shorthand way of indicating the alternative hypothesis. Let's go through one more example, but rather than have a hypothesis looking at the effect of an intervention, what if we think that there's a difference between existing groups? For example, what if we think that male elementary school children have higher behavior problem scores than female elementary school children? For that study, my alternative hypothesis would be male elementary school children have higher behavior problem scores than female elementary school children. What would my null hypothesis be? It would be some version of behavior problem scores for male elementary school children are equal to or lower than behavior problem scores for female elementary school children. So researchers have an alternative hypothesis, which is what they think is going to happen, and they have a null hypothesis, which basically says they're wrong. How do you determine which one is correct? That involves hypothesis testing. But let's stop here for now and continue with our discussion on hypothesis testing in our next video.